Okay, I'm super excited to be here with my really good old and longtime friend, Jan LeCun, who works at Facebook and then NYU as the father of deep learning, so to speak. This is Udacity Talks number 7. We're here in Mountain View Studio, and Jan, welcome.
Nice to have you here. Very happy to be here.
We met, I think, in 1990, which dates us, unfortunately. And while you've kept your hair, I've lost my hair along the way. But you did a thesis on machine learning in 1987 in a small European country called France.
A small European country, yes.
When no one was thinking about machine learning. Like, how on earth did you do this?
I got into machine learning through philosophy. It's a weird story, but I was interested. I was an engineering student, electrical engineering student, and I was interested in intelligence, learning, etc. And I stumbled on a philosophy book that was sort of a debate between Noam Chomsky and Jean Piaget. Jean Piaget is a developmental psychologist that wrote a lot about how children develop. And there was this argument basically between innate and nature and nurture, if you want.
Right.
And on the side of Piaget was an article written by Seymour Papert, the co-author of the book Perceptron, that basically killed the field of neural nets in the 60s.
Because he couldn't learn XOR.
Well, because of various reasons, the limitations were clear in that book. But this debate I was reading about took place 10 years later in the late 70s, and Papert was here arguing for the fact that you could learn things because there was this very simple model, the perceptron, that could learn surprisingly complex concepts. And it's the first time I read about a learning machine, and so I was hooked. I kind of dig the literature, everything I could find on the perceptron, and figured out that all the papers basically ended in the late 60s with that book.
But machine learning at the time was a very active field. Like Tom Mitchell and many others are working on it, and they all use symbolic methods, use things like decision trees and nearest neighbor. Why on earth did you look into neural networks?
Well, it seemed to me that if you want to do perception, that would be kind of a better approach because of the kind of massive amount of data that you would have to process, which at the time was 8x8 binary matrices, right? That was the massive amount of data we had at the time. We couldn't afford to run neural nets on bigger images than that. I just thought the concept was very appealing of sort of trying to reproduce the idea of learning in the brain with synaptic changes and everything. And it was a whole school that had died out. But I thought the idea was very intriguing. It's true at the time, what was fashionable were expert systems on the side of AI, as well as there was a very small sub-community. Tom Mitchell was one member of this, of symbolic learning, and then a completely separate community in pattern recognition, which also had gone to what was called structural pattern recognition, which was basically also symbolic and grammatical inference.
And then you basically invented not just backpropagation, and there's probably 2 or 3 people who claim that, and you're one of them, which is amazing. But you also invented convolutional neural networks at a time when their compute power was so limited. Like, what was the reception of the field to this crazy idea of train something with 1 million data points and 1 million parameters?
Well, so we didn't have 1 million data points or 1 million parameters. We didn't have the computers to run this either. You have to realize also that one reason why it took so long for backprop to emerge is that for backprop to work, you need continuous nonlinearities. You need things that are relatively smooth. A ReLU is not smooth, but things with sigmoids and stuff like that. And back in the old days, computing a multiplication, performing a multiplication on a computer, floating point multiplication, was very expensive. And so people would stick with binary units because it was easier. You didn't have to do multiplies. You just had to do adds and subtract, right? And so I guess it's one of the reasons that backprop didn't come up earlier is the fact that hardware was so limited, and people didn't even think of using continuous.
So did you or anybody else understand the significance of your invention at the time?
The potential, perhaps, but the fact that it was going to work so well eventually, not clear at the time. So what happened there? So during my PhD thesis, I actually implemented sort of locally connected multilayer nets trained with some form of backprop. It was actually closer to what we now call target prop. So instead of propagating gradient, you propagate virtual targets for each of the units in the system. But there is a regime in which those are equivalent, in fact, to backprop. And a number of people sort of came up with similar ideas. In fact, you can trace the idea of sort of backpropagating gradient back to the sort of standard methods in control theory from the 60s for like computing rocket trajectories. So the idea had been around, it's just that people didn't realize they could use them for learning. And so convolutional nets came later. So I finished my PhD in '87, and I did a postdoc at University of Toronto with Jeff Hinton, and that's where I implemented the first convolutional net. But it was kind of a small version of it, trained on a few hundred samples, and then I could scale them up when I went to Bell Labs, and I had a whole Sun 4 just for me.
Yeah, you spend a lot of time on postal data sets. I remember this and all these.
Yeah, that's right.
Handwritten digits on letters
like
for
zip code
almost a decade,
digits.
I guess. Right, it got better and better.
Yeah.
Fast forward, right? So now you're probably arguably one of the most famous people in machine learning. You run a phenomenal group at Facebook. You teach at a college in New York called NYU.
A small school.
So
with 40,000 students.
40,000 students. Tell me, like, what happened? Like, why on earth is it so popular today? Why wasn't it as popular 20 years ago when you invented it? And what happened to you?
Okay, so I kept working on neural nets in the early 90s, and we're pretty successful. We had systems that we built at AT&T that were reading checks, and they got commercialized. And at some point in the late 90s, they were reading something like 10 to 20% of all the checks in the US. So very successful. But the community turned away from those methods, partly because this was before it was very common to distribute your code in open source. It was before the internet, really, early 90s. And so it was before people had common platforms where you could just compile your thing with GCC and just run on another platform. So it was not easy to distribute your knowledge, essentially, like we can do now. And those neural nets are very finicky. At the time, you needed a fairly complex piece of software to make them work, and a lot of investigation, etc. And just building those tools were sort of a big investment. And so very few people figured out really how to do this. And so it kind of died because it was very difficult to use, and it wasn't clear to people that it was worth the effort. So I kind of stopped working on neural nets really for a bit, for about 5 years. Between 1996 or 97 to about 2002, 2001 when I started again. I worked on image compression, and I was also running a group at AT&T, so I had less time for my own research. Right. And I started again when I left AT&T in a big way. That's when Jeffrey Hinton, Yoshua Bengio, and I started the deep learning conspiracy to basically rekindle the interest of the research community in neural nets, because we knew that those methods eventually would work. The whole idea of learning features was obviously a good idea.
Yeah. So, I mean, you have the dream job, obviously. You work in this wonderful lab that you run at Facebook. You get to play with machine learning all day. And many of our students in the world that take nanodegree programs that are listening in right now would love your job, or a job like your job, to say, be more precise. How on earth did Zuck discover you?
You have to ask him. But I mean, he was interested in starting an effort in AI. Essentially, there were a few people at Facebook who had been experimenting with convolutional nets for image recognition, face recognition, various other things, and they were getting really good results. And they talked to Mark, and Mark said that was really interesting. And then he realized that this was just about the time that we're talking early 2013, just about the time that Facebook was about to turn 10 years old. It was, well established on its market, and it was thinking about the next 10 years or the next 20 years. What is it going to be? What is Facebook going to be in 10 years? How are we going to interact with the digital world, with each other, etc.? And he realized quickly that AI was going to be an essential piece of this. And with the quick progress brought about by deep learning, that there was kind of an opportunity there. Cool. So he wanted to start an AI group, and he went around and found the obvious people.
You didn't ask me.
The usual suspects. You were trapped at Google already, I think.
It's true, I was running Google X. Oops.
No, I mean, he went around and talked to quite a few people, but eventually recruited one of my students out of Google X, Marco Ronzetto.
Good guy.
Yeah, and then contacted me and I said, that sounds great. Creating a research lab on AI from scratch. it's probably one of the few jobs I might know how to do because I've been in industry before and I kind of have some idea how to organize this. But and I said, I only have two conditions. I'm not moving from New York and I'm not quitting my job as an academic. And he said, yes. I say, where do I sign?
It's great, it's great. So where does Facebook use deep learning today?
So Facebook uses deep learning for a lot of things, which you don't necessarily see. It's not very visible. So there are things that are very visible, like there is this system for the visually impaired that describes an image.
Mm-hmm.
When visually impaired, connect on Facebook, when an image is shown, it's just vocalized. And that's the visible part. But there is a lot of deep learning that's used in the background to rank content. So every time you connect to Facebook, Facebook can show you 2,000 or 3,000 items per day, and you don't have time to look at all of this.
I don't.
I'm sure you don't. Yeah, I don't either. Even though I spend a lot of time on Facebook, believe me, because we use it internally as our discussion group, basically. But Facebook needs to show you maybe 100 or 150 items every day, and it needs to select the ones among the 2,000 or 3,000 that are most likely to interest you. So it needs to understand content and understand people's interest, and then match the two.
Right.
And that's basically all deep learning.
So we often take questions from the audience. We have an online audience that asks questions. We have an in-person audience tonight. But Calvin online asked a question: where do you think the future of AI will be in 5 to 10 years? Okay, well, if the things that we're working on actually pan out, I can tell you what I hope will happen if those things work out. So there are essentially 2 or 3 areas that we're working on, general areas. So one of them is, I guess, something you could call differentiable computing, which is the idea that you can implement pretty much any operation that a computer would do or a person would do by reasoning, like an expert system applying rules would do, in terms of differentiable operations, where you would replace logic by algebra, you would make everything differentiable, so that would allow a machine to essentially learn complicated sequences of actions by being shown examples. That would be very useful, for example, for training dialogue systems that can, talk with a person in sort of a natural way, and perhaps be considerably more useful or smarter than the current virtual assistants. That's one area, and the other area. So my future lawyer will be a Facebook AI system. Possibly, yeah, possibly. I'm looking forward to that day. Yeah, my future lawyer will be my oldest son. But so the other area, which I think is also very important and very key to making significant progress in AI, is to get machines to acquire common sense. So it's an old question that AI people have asked themselves. AI systems don't have common sense, and so the ability to for a machine to have common sense essentially relies on those machines being able to learn how the world works. And the way we learn how the world works is by living in it. It's by observing how things work. And we learn what's possible, what's not possible, by just observing how the world evolves, what can happen, the physical constraints of the world, and things like this. And how do we get machines to do this? And so I guess in the field we would call this unsupervised learning, or maybe predictive learning. Basically learning with data that has not been annotated by humans in such a way that the machine can learn sort of forward models of the world. Right? So the essence of intelligence, in my opinion, this is a very personal opinion, not everybody needs to agree, but the essence of intelligence, I think, is the ability to predict. If you can predict how the world is going to evolve because the world is the world, or how it's going to change because of your actions, then that means you can plan ahead and act in an intelligent way. And so how do we get machines to learn to predict? That means you also get lots of data for free, because all you do is wait a few seconds and then you have the training data. Exactly. So one of the things we're working on is video prediction. So here is a snippet of video that we show to a machine, and we ask it, what is the world going to look like a quarter second, a half a second from now, maybe a second, maybe an hour from now? What is Facebook predicting for the US presidential election at this point? Facebook is not predicting this kind of thing. I wish you could. Love to see a bit more in general intelligence. So do you think, so there's this camp in artificial intelligence that says, okay, it has to be specialized. Like you can play Go, but your Go playing computer won't be able to drive your car. And then there's people who say we're going to get this thing called general AI, which kind of outsmarts all of us in every dimension. Is that in reach?
AGI, right? Artificial General Intelligence.
Correct.
So I think, I don't know if it's in reach. My picture of this, my analogy would be, we are in a landscape on the way to AI, and we see a mountain, and the mountain I'm seeing right now is this problem of learning forward models. So, basically having a machine learn by observation and maybe by action as well. And that's the first mountain. We don't know how many mountains are behind it. And so it's easy to be optimistic, like generations of AI researchers before us who predicted that, machines would be more intelligent than people by, 10 years from now, 15 years from now, 20 years from now. And they were all overly optimistic. And so the reason they were overly optimistic is that you have a set of technique, you don't see the problems yet until you hit a wall or a mountain. So we see one mountain, we know we need to get behind it, we don't know how many mountains there are behind.
Interesting, interesting. We have literally hundreds of students that send us questions, and I have a big stack of questions here which I can't all read. But several of them ask, basically, what does it take to become a member of your group? Like, what qualifications do people need? Do they really need a master's degree, a PhD? Maybe a nano degree from Udacity is sufficient, perhaps. They're very small. They're like the small nano degrees.
Okay, so there are several roles at Facebook AI Research. So Facebook AI Research is roughly 2/3 research scientists and 1/3 engineers.
Okay.
And the research scientists are all people with PhDs. And we generally only hire on a permanent research scientist after postdoc.
Mm-hmm.
So people out of PhD we hire as postdocs, and then we kind of make them permanent eventually. The engineer population is much more diverse in the sense that there are people with PhDs, there are people with masters, there's people with just a bachelor, and there
with
are
nano degrees?
And there could be people with nano degrees if they have done something that we think is interesting. So you've contributed to like something really interesting to some open source deep learning stuff, or you made a project that looks really impressive. Your degree doesn't matter at that point. It's really your contribution, your expertise.
So you look at project portfolios occasionally and look at what people have done, and that is a factor in hiring.
I mean, we look at this for anybody we hire. It's not always the case that people have things that are visible like this, but it's a very important track record for us. If someone has contributed to an important open source project in a good way, that's
good.
It's a good indication.
Dimitri is asking online, in your opinion, areas in the workspace or corporate world that will be most affected by AI-powered technologies in the next decade or so?
Well, so obviously all the web industry is, very, very active in the domain, but in everybody's life, I'm not going to have to convince you that it's going to have a huge effect on transportation, on medicine. You've been working on both of those things, so. And those are probably the most visible effects, I think, that people will see over the next 5-10 years of application of deep learning and AI.
Chain is asking a question, which I also have, by the way. I'd love to hear your answer to this one. What is the main bottleneck of deep learning, and what may be the next big thing in this field? So
unsupervised learning, as I said before, I think that's really the big bottleneck. Right now, we have to, 95%, when I say 95%, it's, I'm sort of pulling this number out of thin air. It's probably higher than this. Most applications of deep learning today, most applications of machine learning today, all use supervised learning, right? So you train an image recognizer, you show it thousands of images, and those images have been labeled, and you tell the machine what the label is, and if it makes a mistake, you correct the parameters. But that limits the amount of information that the machine has access to per sample. So training a machine to do things like video prediction, for example, would allow it to learn a lot more about the world, and that's really where the bottleneck is, I think, at the moment.
That is kind of supervised, right? Because you could say you look at the last 20 seconds of video, you take a little break, bathroom break, and come back 10 seconds later and predict the frame then, right?
Here is a difference, though. It's prediction with uncertainty.
Yeah.
So if I put that pen, if I hold this pen in my hand and I let it go, it's going to fall, but you can't predict which side is going to fall. And every time I do it, it falls in a different direction, right? And so if you use a supervised learning algorithm to do this prediction, and your supervised learning algorithm, your convnet, deconvnet, whatever it is, predicts this, and the world actually does that.
And the mean might be that it stays up there, right?
Well, there is a small probability
Yeah,
for that to
mean
happen,
outcome.
possibly.
No, but the mean outcome from all the falls is going to stay up.
No,
It's non-convex.
the mean outcome is an average of all of the positions of the pen
Okay,
in
good.
all
Here we are.
things. So what you get is a transparent pen, in all position, which is not a good prediction, right?
That's true.
So if you use a normal, supervised learning with least square to do this prediction, that's exactly what's going to happen. It's going to predict the average of all the possible futures, which is not a good future. So what you want to tell the machine is you want to tell it, okay, the data tells you this. In this particular example, you predicted that. It's conceptually correct. So how do you train a machine this way to tell it, even if the answer you produce is not the exact correct one, it belongs to the family of plausible futures.
Mm-hmm.
And one of the promising approaches that we're working on to solve this problem is something called generative adversarial networks. So this is an idea that came up.
Generative adversarial
networks. GANs.
Watch your Facebook feed because you're going to have a generative adversarial network popping up on you if you don't look out for you.
Right, exactly.
Like who chooses those names?
This idea came out of Joshua Bengio's lab. This is a paper by Ian Goodfellow, who is now at OpenAI.
Okay.
And this idea that essentially, you can interpret it in several different ways. His interpretation is probabilistic, but you could think of it as you train a predictor or a generator, and you have another network which is basically a trainable objective function, trainable loss function. And what this other network learns is the set of possible predictions that are correct, even though the actual prediction by the generator network may not be exactly correct. And those two networks train against each other, which is why it's called adversarial training.
I hope you guys change the name before we release it to the public. I don't want to.
It's not mine to change. Unfortunately,
general adversarial networks at Facebook, but it's a great idea.
I think frankly it's the best idea in machine learning in the last 10 years.
Interesting. We should teach it. Are we teaching it? Not yet,
I
guess.
You should.
We'll teach it. Okay, we come back and teach.
I teach it
general
in my deep learning
sure
course at NYU, yes.
But we teach more students than you do, yes. That's our advantage. You might be more up to date. I want to have an audience question here. Anybody has a question here? Yes, please, Dhruv.
So outside of deep learning, is there anything else that Facebook AI works on? And are there other technologies that are in resurgence once we found out about new capabilities of computers and GPUs that we've ignored, just like deep learning was ignored for so long?
I hope people will come up with, the successor to deep learning. I think the whole idea of assembling learning machines by assembling modules and using sort of gradient-based learning, that's not going away. So in that sense, deep learning is not going to disappear. It's just going to become, just another tool. But I think what people are working on now is, different types of architectures, different training procedures. This adversarial idea is very new in the sense that it breaks the model that we're used to in machine learning where we minimize some loss function. Here we're actually finding a saddle point of a function, and it's very complicated. There's a lot of things we don't understand, things don't converge and we don't know why. So, but when it works, it's amazing. So there are a lot of things like this. So I think deep learning is part of the toolbox. Almost every system we put out have some deep learning in them. But a lot of people are not working specifically on deep learning. They're using deep learning for applications like natural language understanding, computer vision, speech recognition, translation, things of that type. There's people working on causal inference. There's people working on sort of the applied math type side of things, optimization, large-scale SVD, fast nearest neighbor. There's a lot of techniques like that.
Ali asked a question online asking, how do you apply deep learning to very sparse data, like small sample sizes and sparse matrices? Okay,
so data can be sparse in two ways, right? It can be sparse in the sense of not having many samples, or it can be sparse in the sense of having a high-dimensional input where most of the values are zero, right? And that's a situation that's very common in
but people, you can give me one data point of your favorite pen, and I'm able to recognize this pen from no viewpoints even after one training data.
Right. Well, but that's kind of ignoring all the learning that you've done before.
Right. Yeah, but how do you get deep learning to become such a versatile learning machine that you can just give it one example and it's still useful? So
there's such a thing called transfer learning, right? And people have done this with ImageNet is actually a product inside Facebook that does this, where you train a convolutional net to recognize images on whatever categories that you have in your training set, the largest number of categories possible if you want. And then what you have is a network that can basically represent any image. So at the top layer or the second last layer, it has a feature vector that you can use for just about any recognition task. And so take this vector, plug it into your favorite classifier, which can be very simple, well regularized. And with just a few examples now, you can recognize a new category. In fact, that's how face recognition works at Facebook.
Very, very cool. I have to ask you, so other people like Elon Musk have talked about how artificial intelligence is the most dangerous thing we ever developed, and he wants to go to Mars to escape it, and then Stephen Hawking has made some interesting predictions about it. So has Bill Gates.
Yeah.
Where on the spectrum of like complete paranoid to absolutely optimistic, where do you stand?
Cautious optimism.
Cautious optimism, what does that
Yes.
mean?
Okay, what that means is that I don't
optimism.
think we're going to build dangerous, humanity-threatening or sort of, existence-threatening AI systems by accident. I mean, it's hard enough to get them to just, drive on a highway without,
Now, that could be a humanity-threatening device, a improperly trained highway car.
Yeah, but it won't destroy all of humanity, I think.
Just some.
Perhaps just a few, a limited number of people, hopefully. But so there's the paperclip scenario, right, where you build a machine whose only purpose is to build paperclips, and all of a sudden it's so smart that you convince yourself not to turn it off, and it turns the entire galaxy into paperclips. So this is the Nick Bostrom scenario in his book Superintelligence, and this is a book that all of these people that you mentioned have read and have told themselves, oh my God, we need to be careful. I don't believe in this scenario. I mean, there is this would be kind of like building a self-driving car with a 1,000 horsepower engine. The throttle is all the way through, and you can't remove it. There is no brake and no safety belt. Nobody would buy it, first of all.
That's true.
So cautious optimism in the sense that I think there are relatively simple way to build machines in such a way that their intrinsic motivations are aligned with human values. So how to do this in detail is really not entirely worked out. But in my opinion, we have at least 20, 30, maybe 50 years to think about it, because we just don't have the technology to build super intelligent machines, or AGI, as you were mentioning before. That's going to take decades.
You think it's decades out, I see.
Yeah.
So do you think we are in a singularity right now when it comes to AI, or is it too premature?
Well, I think we are in a fast evolution, which is overdue. So my expectation, when I started getting in this field, is that we're going to have some sort of continuous evolution. Turns out that there was some evolution and then a plateau for 10, 15 years, and now
it's because you stopped working on neural networks, right?
It's not because of that, it's because the entire world stopped working on it. Some of my friends said that if I had gone to academia and had a following with students and stuff like that, maybe it would have been different. I don't know. If I had gone to academia earlier, I don't know if that's true. So I don't believe that we're in a singularity. There is nothing that looks more like an exponential than the beginning of a sigmoid. And in every physical process or social process, there's friction, which initially those friction terms don't matter, you don't see them. But eventually when things start picking up, the friction terms start getting non-negligible and eventually take over, and that's what creates saturation. Yeah. So I don't believe in the whole concept of singularity, really.
Right. I want to ask one last question before I close down, and that pertains to our students. We have many, many students online, and some in our room here, and quite a few come to us at Udacity because they want to basically get a better career and want to get into machine learning. And our goal, of course, has been to empower this. These are students in all countries and all genders and all ages. So my question would be, what piece of advice would you give to a student, say, who grows up in India or Bangladesh or South America?
Well, I think it's a great time to be a young student who is really fascinated or interested by this kind of technology. Now you have access to data. Computers are relatively cheap. Access to information is ubiquitous. When I was growing up, it wasn't like that. I was, kind of a nerdy, kid, and I was fascinated by technology already at a young age, science and technology in general. So were you, and And you know, I was building stuff, you know, building electronic things and airplanes and stuff like that. And you know, bought my first computer. I was 17, and this was 1977. So taught myself assembly programming because there was no alternative to it.
Me too.
Right.
Painful.
Yes. So
I was very proud I was able to do this.
that's right, and it was, you know,
Like LaTeX.
complicated, expensive, etc. But you know, you could buy magazines and learn about this there.
Yeah.
That was the equivalent of Udacity. Now, of course, things like Udacity.
Open
and
source meant you put your assembly code into a magazine, right?
Yeah, that's right. That was the idea of open source. Then you had to like type it in.
Yeah, you copy it over.
and then save it to a cassette player.
Yeah. Which I couldn't afford. So I had to do it every single time from scratch.
Right. Yeah. Yeah. Me too. So I think it's a great time to be you know, young, motivated student. You can play with the, you know, with the greats, and you can make contributions, and so you don't need to be shy. And you'll be recognized if you make contributions to the open source world. That's a wonderful vehicle for showing what you can do.
Yeah, and I'm so delighted you're here. I can imagine that
Pleasure.
we met, 25 years ago,
Something
26 years ago, and it's
Yeah.
great to see you so successful at Facebook and changing the world. Thanks for coming. To our students, this is our, I think, 7th version of Udacity Talks. Again, Jan LeCun, Director of AI Research at Facebook, Professor at NYU, and all around a wonderful human being. And I see you next time, hopefully, with our technology working. Thank you.